So let us start today's session, sir. So under engineering mathematics, we were talking about linear algebra. In today's session, we mainly talk about square matrices. Now things are fine, sir. Now, am I audible, visible to all of you? Yeah. So let us start today's session here, sir. Elementary row operations. See, these are the, you can say, the most important operations, or you can say heart of this entire linear algebra. Most of the work which we do in linear algebra is based on this elementary row operation. We also have elementary column operation, but we try to restrict ourselves to row operation most of the time. Maybe for this elementary matrices concept, we try to discuss both row as well as column operation, but most of the time we talk about only elementary row operation. Okay? Yeah. Good morning, sir. Okay? What are these elementary row operations? Interchanging two rows. This is one. The second one is multiplying a row with a non-zero constant. We are multiplying a row with a non-zero constant and k should be non-zero, my dear friend. Adding a constant multiple of other row. Suppose this is the row. We are adding constant multiple of other row. Constant multiple of Rj is added to Ri. So this is what you mean by elementary row operation. See, in the similar lines, we can also have elementary column operations. We can also have elementary column operations. What are the elementary column operations, my dear friends? The elementary column operations are, the first one is interchanging two columns, multiplying a column with a non-zero constant. K should be non-zero. You can mention that clearly. In mathematics, always it is very important to mention the properties properly. And the third one is adding constant multiple of other row to this row. So these are the elementary column operations. Okay. Now let us try to apply these elementary column operations on this particular matrix. See here, I am just applying. Don't worry about why we are doing it. See, the biggest problem with most of the students is they immediately want to do some applications. It won't work like that, my dear friends. We don't have one-to-one correspondence for every mathematical concept. There are some concepts which are used for developing some other concepts which are useful for application. Okay, so it happens in that manner. Please remember. Okay, see here, I'm just doing. I'm learning the row operations. I interchange row 1 with row 2. So it is not same as the original matrix. Okay, it is a new matrix. After interchanging, you get a new matrix. This is the new matrix. 1 1 4 3 3 2 1 4. That is, the first row becomes second row and second row becomes first row. Swapping of the two rows. 2 1 1. So this is what you mean by interchanging two rows. Now let us do one more row operation. I want to multiply a row with a non-zero constant. So let me multiply row 3 with 3. 3 times row 3. So once you do it, I get a new matrix. First row as it is. Second row, no changes. And in the third row, we are multiplying third row with 3. 3 2 6, 3 1 3, 3 1 3, 3 2 6. So this is the idea, my dear friend. Okay. This is the second row operation. Now let us perform the third row operation. The third row is adding constant multiple of other row to current row. See, what I am doing is I am trying to use this row operation to make this fellow 0 using this element. This is generally what we do. So how to make this fellow 0, sir? R2 is R2 minus. If I multiply with 3, the first row, and subtract from second row, I am going to get, I can make this fellow equal to 0. So that is exactly what I am trying to do. First row as it is, no changes. Second row, 3 minus 3, 0. Please be careful. Most of the people, they do this operation only for this element and they leave them as it is. That is the biggest blunder. Good morning. Okay. So now what happens? 2 minus 3 is minus 1. 1 minus 12 is minus 11. 4 minus 9 is minus 1. The third row we are not doing anything. So these are the elementary row operations. In the similar line, we can also perform elementary column operation. Okay. See, strictly performing a row operation means swapping of two rows or multiplying a row with a non-zero constant or adding a constant multiple of other row to this row. These are the strict elementary row operations. Sometimes that is what I done, no? Anshuman Cheney. R2 minus 3R1 only I done it, no? Acha, you want to do R2 is minus 3R1. That cannot be done. If you want to do this, this is blunder. There is no such row operation. Okay. So that is not elementary row operations. You can't make one row is some other row. No, no. It cannot be done. You have to use the current row and you can add some constant multiple of other row. You can't just change one row to the other row. You can swap rows. Am I clear? That cannot be done. But one thing can be done later on for some applications, not for all. We can make combination of the two row operations. For example, second and third row operations can be combined, and sometimes you may do like constant times Ri plus some constant times Rj. That can be done, sir. That can be done. 2 by 3, that can be done. This can be made 1. Yeah, you can do R2 is 2 by 3 times R2 minus R1. This can be done. This can be done. No problem. Okay, that can be done because, but that is of no use, na? Because of that, you are going to get 2 minus 1. You make it 1. You want to make it 0. That's why I am doing this operation. This can be done, no problem. But it is of no use. See, my purpose is to make this element equal to 0 using this element. So for that, this is the best row operation. Okay, or you can do this instead of 2 by 3, now you can do 1 by 3 R2 minus R1. My dear friends, working with fractions is laborious work. So we generally avoid that. That's why we try to use the integer multiplication. Okay, that's why we also use this particular combination of second and third row operations sometimes to make our life easy. Okay, remember. Now one very interesting concept. Okay, this is a very interesting concept. If you are very much interested in the factorization method like LU factorization, they are all based on this concept. Of course, I'll be giving it as a trick when I discuss LU decomposition, but the internal story is coming from here. Okay. What about elementary matrices? See, you all know identity matrix. On a identity matrix, if you perform a single elementary row operation, no combination, single elementary row operation or single elementary column operation, the new matrix which is obtained is called elementary matrix. Now consider this identity matrix. Okay, I take a 3 by 3 identity matrix. You can perform a single row or a single column operation. Suppose I perform R2 and R1 interchange. So this matrix which is obtained, that is second row becomes first row becomes second, third row as it is. See, this is called an elementary matrix. By performing a single elementary row or single elementary column operation, if you get a new matrix, that matrix is called elementary matrix. Of course, you have to apply it on identity matrix. That is a matrix obtained from identity matrix by performing single elementary row operation or column operation is what is known as elementary matrix. Now look at this matrix. Again, I take identity matrix 0, 1, 0, 0, 0. Now I am performing following column operation. Column 3 is column 3 plus 2 times column 1. See here, first column as it is, second column as it is, third column 0 plus 2 times. So here it is 2, 0 plus 0, no change, 1 plus 0, no change. Now identifying elementary matrix is one of the important tasks, my dear friend. That is, if I give this matrix, can you identify whether it is a elementary matrix or not? If I give this matrix, Can you tell me whether it is a elementary matrix or not? That is wonderful work, my dear friend. Okay. So let us try that. Of course, you can try some more examples on this, my dear friends. See, when you interchange two rows, you can easily identify, sir. When you interchange two rows or two columns, you can easily identify. For example, if I write this, you can easily identify it is elementary matrix obtained by interchanging first and third rows, yeah, first and third column. And elementary matrix obtained by multiplying any row or column with constant is also very simple. For example, if you observe this is very simple to observe that because only this element is changed. That is in the main diagonal, only one element is changed, means it is obtained by multiplying a row or a column with a non-zero constant. This is obtained by second type of row or column operation. Now this is very interesting. Identifying this is very interesting. Now look here. Now if you are doing row 3 is equal to row 3 plus some constant times either row 2 or row 1. Suppose if you are doing constant times of row 1, that constant will occur here. If you do constant times of row 2, that constant will occur here. This fellow will be as it is. So this is obtained by row 3 is row 3 plus some constant times row 2. Suppose instead of C here, if you get C here means, if C is here means, that means you done constant times row 1. So given matrix, whether it is elementary matrix or not, identifying is one of the important tasks, and it helps in identifying inverse of the matrix very quickly. And there were GATE questions based on that. I'll give you a wonderful rule. You can call it as a shortcut or a trick. Which of the following is elementary matrix? Now I given 4. Of course, there can be multiple select question also it is. Please write down your answer. Which of the following is elementary matrix? A, B are the elementary matrices. Very good. So here you can see only this element is changed. It is obtained by either second row or second column operation. Here what happened? The second and third rows are interchanged. So it is also elementary matrix. This is also elementary matrix, my dear friends. Here it is R2 is R2 plus 2 times of R1. It is also elementary matrix. This is not an elementary matrix because you see two elements in the main diagonals are changed. That cannot be elementary matrix because you perform two operations. 1, 2, 3. A, B, C are elementary matrix. D is not. See, my dear friends, if you write only half answers, you will not get marks. You have to write full. You have to write all 3 options correct for multiple choice question. Okay, even if you write 2 correctly, you will not get marks. Remember. Now the interesting thing is all the elementary matrices, whatever elementary matrix you get, they are all invertible. Inverse of such matrix exists. And inverse of elementary matrix is also an element. If it is elementary matrix, the inverse is also another elementary matrix, and you can easily identify. Now look at this. Suppose your elementary matrix is obtained by interchanging 2 rows. The inverse of the elementary matrix is the same fellow. For example, this was a GATE question. Okay, they asked this. They given this matrix and they asked you to find A inverse. Okay, different options, A, B, C, D options were given. This was a GATE question. And you know how people solve this? Adjoint A by det A. Tomorrow morning you will get the answer. But here, if you observe that it is an elementary matrix obtained by interchanging 2 rows, the inverse of this matrix is same matrix. You got the answer within no time. That is the advantage of knowing the result. The shortcuts are just results. You just understand the result, shortcuts automatically. That is what happens in mathematics. Now suppose if you obtain an elementary matrix by multiplying a row or a constant or column with a non-zero constant, the inverse of the matrix is that constant you have to replace by 1 by k. Wherever k is there, no, the k has to be replaced with 1 by k. For example, you see 1 0 0 0 4 0 0 0 1. This is the matrix, elementary matrix. What is inverse of this? Everything is same. This element is replaced with 1 by 4. And if elementary matrix is obtained by third type of row or column operation, the inverse of the matrix is wherever k is there, that k has to be replaced with minus. If, for example, if you see this, we don't have this. Okay, this example. If you want to find inverse of this matrix, only this 2 has to be replaced with minus 2. Remaining things are same. That is the inverse of this matrix. Directly we can answer the. Hope you understand. So you can see this example. What is the answer? What is the inverse of this matrix? What is the inverse of this matrix? What is inverse of this matrix? Same. Because it is obtained by interchanging of which rows? It's obtained by interchanging of which rows, my dear friends? First and second rows. What about inverse of this matrix? Inverse of this matrix is obtained by just replacing this 3 with the diagonal matrix. Now you can happily write, instead of writing the entire story, you can write 1 1 and 1. See, whenever it is identity matrix, now we can write DIAG diagonal, that main diagonal elements you can write. Not only identity, any diagonal matrix, we can simply write main diagonal elements because remaining all elements are 0. Very good. No, first and not first and second, only seconds. Okay, okay, very good. That is the answer for previous one. That is the answer. What about inverse of this? Which number will be replaced with what? Okay, please tell me which number is replaced with what. Now what about this? Here 1 0 0 0 1 0. This my 2 is replaced with minus 2. This is what. Okay. So you can easily answer the question. Right. Now let us take one more interesting concept. As I told you, matrix is a general tool. Okay, it can be used for variety of purpose. And matrix is one of the matrix and determinants are the important rules for linear algebra. Okay, the study of system of linear equations. Not only that, matrices can also be used to represent vectors. Vectors in n dimensionals, 2-dimensional, 3-dimensional or n dimensional. Suppose you are having a vector in n dimensional space, it can be represented as a ordered n tuple, or you can represent it as a column matrix or row matrix. See, if a vector is represented as a column matrix, we call it as a column vector. This is column vector. And if it is represented as a row matrix, then it is called row vector. That is a terminology, my dear friends. See, these 5 important definitions which I am going to give, which are very, very useful throughout this linear algebra. Okay. For a vector, what is the length of the vector? What is the length? See, if you are having any vector in 3-dimensional or any n-dimensional space, what is the distance from length of the vector means distance of that vector from origin. Okay, and you all know the distance formula, under root x1 square plus x2 square, that is component square you have to add and you keep it under root, you are going to get the distance of the vector from origin. Am I clear? So this is the distance formula only. See, actually up to 3 dimension we use mod x. Higher dimension we use norm. This is called norm x. For higher dimension vectors we use norm instead of length mod x, we use norm x. So under root x1 square plus x2 square and so on x square, my dear friend. So that is the length of the vector. And Suppose if there is a vector whose length is equal to 1, we call such a vector as unit. For example, consider this vector, sir. 1, 2, 3. What is the length of the vector? Norm is a special terminology used for length of the vector for higher dimension vectors. Up to 3 dimension, we use mod x only, but higher dimension vectors, we use norm. Norm means length of the vector. Norm means length of the vector. Length of the vector. Okay. So, what is length of this vector, my dear friends? Under root 1 square, 2 square, and 3 square. So, 9 plus 4, 13 plus 1, 14. Under root 14. Okay. Now, look at this. 1 by root 2, 0 minus 1 by root. What about the length of this particular vector? 1 by root 2 whole square, that is 1 by 2. 0 square, that is 0. 1 by minus 1 by root 2 whole square, that is 1 by 2, which is nothing but under root 1 any 1. So, this is unit vector, but this is not a unit vector. This is unit vector, but this is not a unit vector. Okay. Now, look at this vector. This is feeling bad. I am not unit. Okay. You can create a unit vector. See, it is just finding a unit vector in the direction of a vector. How to get unit vector in the direction of vector? Divide the vector by its magnitude. That is what it is. Normalizing a vector means getting a unit vector in the direction of a vector. This is what you mean by normalizing. So, you can take this particular vector x and you can normalize. Normalize x is equal to 1, 2, 3. See, if it is unit vector, no need of doing anything. But if it is non-unit vector, what do you mean by normalizing? First, find the length of the vector. The length of the vector is root 14. So, normalized vector is the vector is obtained by dividing the vector by its magnitude. That is, each component is divided by root. Even there was a question asked in GATE. They asked, what is the normalized vector for a given vector? Those who don't know that normalizing means finding unit vector in the direction of vector, they left the question. Otherwise, you can easily answer such question. Am I clear? See, they expect you to know the basic concepts, so they can ask you question from anywhere. That's why you can find different types of questions in GATE examination, starting from very basics, and you can go to very complicated questions. I shown you just now elementary matrices. Two of the questions were GATE questions. If you understand it is elementary matrix, it is just one word answer. If you don't know it is elementary matrix, still you can get the answer by adjoint A by det A. That's it. Next, for vectors, we can also find the dot product. It is not the product of the vector because you cannot find product of two vectors, two column vectors. It is dot product. How dot product is defined, my dear friends? The dot product of the vectors x and y is defined as just multiply the corresponding components and that is the dot product. And you can get the dot product in terms of product of vectors. For that, you have to take transpose of the vector x and multiply with. This is dot product of two vectors. Dot product of two vectors. And if the dot product is 0, then we call them as orthogonal vectors. If the dot product is 0 and both the vectors are unit vectors, then we call them as orthonormal. Okay. See, my dear friends, we are going to discuss about this orthogonal vectors, orthonormal vectors. If you study eigenvectors, they all come under that particular. Okay. Suppose you are interested in orthogonal diagonalization process, there you will be using all these concepts. But we will not go up to orthogonal diagonalization. But this idea, the idea of this orthogonal vectors and orthonormal vectors plays very, very important role in identifying whether the matrix is orthogonal matrix. Okay, for some other purposes they are definitely. Am I clear? So these are all the vectors which you are going to use in particular linear algebra topic. Okay, so you understand what is dot product. Suppose you are having a vector x and another vector y. What is their dot product? Just multiply corresponding components and add 1 into 2 plus 2 into minus 1 plus 3 into. So what is the answer? That is the dot product of those two vectors. dot product of those two vectors. See, this is how we can get dot product in terms of matrix product. X dot y is equal to X transpose into y. If you want to write dot product in terms of matrix product, this is the method, my dear. And if the dot product is 0, then the vectors are called orthogonal vectors, and both the vectors are unit vectors, then we call those two vectors as orthonormal vectors. For example, let us consider 1 by root 2, 1 by root 2, or let us take a better example, a silly example. So let us take a better example, cos theta minus sin theta, and let us take y is equal to sin theta and cos. Now let us try to find the x dot y. The dot product is cos theta sin theta minus sin theta cos theta, which is 0. What is length of x, my dear? Length of x is under root cos square theta plus sin square. Under root cos square theta sin square theta is 1. Similarly, length of y is also, length of x is 1, length of y is also. So here these two vectors x and y are called orthonormal vectors. These two vectors are called orthonormal vectors. Now I'll give you one more example. 1 minus 2, 2, 1. Now take the dot product of these two vectors. What is dot product of these two vectors? The dot product is 0. They are orthogonal vectors. The vectors are orthogonal, but they are not orthonormal, my dear. You can try this example. Find length of each vector. Length of each of these vectors, my dear. Please try finding length of each of these vectors. What is the specialty of Z? Please tell. What is the specialty of Z? Please. So you can easily observe the length of Z is 1. Okay. Length of Z is equal to now here given two vectors and they say that these two are orthonormal, and he is asking what is the value of this. These two vectors are orthonormal, what is the value of A? Okay. So let us see this, my dear. See, when there are orthonormal vectors, two things. Suppose you call one of them as x, the other one you call it as y. The length of x should be 1, length of y should be 1, and their dot product must be equal to 0. All the three conditions must be satisfied, sir. Okay, don't take the value of A which satisfies only one condition. You have to consider the value of A which satisfies all the three conditions. Orthonormal means all the three conditions, not just one condition. See, this is where most of the people misunderstand the concept. Okay, orthonormal means this. For example, if you consider this, you get two values of A. But if you consider this, you get only one value of A. But you have to consider the value of A which satisfies both the conditions. And that is the value I am going to. Okay, so I am going to consider this x dot y is equal to 0. What is the dot product, my dear friends? Denominator is always 7 into 7, that is 49. Numerator 3 to 6 minus 18 plus 6a, and this must be equal to 0. That is 6a minus 12 is equal to, and a is equal to, actually if you try length of the vector is equal to 1, you get under root, denominator is 49, numerator is 3 square, 6 square, a square, and this should be equal to 1. So what does it mean? Under root, you can just keep this value here. This is 45 plus a square under root is equal to under root 49. That means a square is equal to 4, means a value should be either plus minus 2. Now people worry about it, whether we should take plus 2 or minus 2. See, plus 2 satisfying both the properties, so we consider a value to be plus 2 only, not minus 2. A cannot be minus 2. Okay, now we'll try to discuss some very important special square matrix. Okay, so let us start with the discussion of square matrix. And what do you mean by square matrix, my dear friends? A square matrix is a matrix having number of rows equal to number of columns. Okay, this is how we denote square matrix. Now, what are the very important square matrices? Of course, here I am going to discuss few important square matrices like triangular matrices and symmetric, skew symmetric, Hermitian, orthogonal matrix. Then the complex analog matrices for those, that is Hermitian, skew Hermitian, and unitary matrix. Later on, we also discuss the idempotent and other square matrices when we discuss determinants, my dear friend. Okay. Now let us consider special square matrix. The first one is triangular matrix, or let us write down the name. First one is upper triangular matrix. Upper triangular. The upper triangular matrix. What is this upper triangular matrix? The upper triangular matrix is a matrix, square matrix, with the condition Aij is equal to 0 for all. I'll give you option: I less than j, I greater than j, I equal to j. Don't know. Of course, you cannot write don't know here. I just given don't know. What is the answer for that? What is upper triangular matrix? I less than j, I greater than j, I is equal to j, or none of them? See, many people know what is upper triangular matrix, so they can write down what is upper triangular matrix. So, in upper triangular matrix, using double subscript notation, I am writing A11, A12, A13, 0, A22, A23, 0, 0, A3. Now, if you observe this particular element, this is actually second row first column element. That is, when I is greater than j, it is becoming 0. The condition is I greater. If you simply write a simple 2 by 2 upper triangular matrix also, you can understand what is the condition for this matrix. So, this is upper triangular matrix. That is, all the elements below main diagonal are 0. The condition is Aij is 0 for all I greater than j. The next one, lower triangular matrix. Lower triangular matrix. What is a lower triangular matrix, sir? It is also square matrix with the condition Aij is equal to 0 for all. Can you tell me what is the answer for this? What is the answer for this? Just now we done na? For upper triangle, if it is I greater than j, for lower triangle, it should be I less than j. Na? We also have diagonal matrix. The diagonal matrix is denoted, it is also a square matrix. The condition is Aij is equal to 0 for all I not equal to j. For all I not equal to. Now, I always have this particular doubt, my dear friends, whether it is diagonal or not. Whether this matrix is a diagonal matrix or not. Please check the condition. See, you don't have to worry about it. What it says, Aij is 0 for all I not equal to j. That is, other than main diagonal, remaining all elements must be 0. There is no condition for main diagonal elements. So, people create their own conditions. It is diagonal. People create their own condition that diagonal should not be 0. Is there any mention for that? Okay. This is how we misunderstand definitions in mathematics. Okay. We need to understand definitions properly. Okay. It says Aij is equal to 0 for I not equal to 0. We call them as off diagonal elements. Other than main diagonal, remaining all elements must be 0. That is the idea. Remember. Next, the most important 3 square matrices called symmetric, skew symmetric, and orthogonal matrix. Then we try to discuss their complex variants. Okay, not corona variants. What is a square matrix? A square matrix symmetric matrix. What is a symmetric matrix? A square matrix A is symmetric if the transpose of the matrix is equal to A. What do you mean by transpose of the matrix is equal to A, sir? The condition is ith row jth column element must be same as jth row ith column. This is what you mean by symmetric. So if you write the matrix, you can consider this main diagonal as a mirror. So whatever element here, find same element. The ith row jth column is same as jth row ith column element. That is aij and aji are mirror image. That is whatever elements you find, the same elements you find, the mirror images you can find. That is, you can just consider this as a mirror. You find the mirror images here, my dear. Okay, so that is what you mean by symmetric matrix. Now I given a matrix, I say it is a symmetric matrix. Then what about the values of A, B, C? You have to tell me what is A. So once it is a symmetric matrix, this is your main diagonal. So A must be 4, B must be 2, C must be. So you can easily find out values of A, B, C when you know it is a symmetric matrix. Next comes skew symmetric. What about skew symmetric matrix, my dear? A skew symmetric matrix is a square matrix satisfying the condition transpose of the matrix is equal to minus of the. Now here there are two conditions. Here we are having two conditions. First one, A transpose is equal to minus A means Aij must be equal to minus Aj. So actually if you consider main diagonal elements, Aii must be equal to minus Aii. That means 2Aii must be equal to 0. Therefore, the Aii must be equal to. That means main diagonal elements are 0. Main diagonal are, or all main diagonal elements are 0. Okay, that is about skew symmetric matrix, my dear. Now this is a skew symmetric matrix. He is asking what about the values of A, B, C, D. See, once it is a skew symmetric matrix, the main diagonal fellows becomes 0. A becomes 0 and E becomes 0. And off diagonal elements like B, C, D, B value will be minus of this. C value will be minus of this and D value will be minus of this. That is what you mean by skew symmetric matrix, my dear. Now, if A is a square matrix, then which of the following is R symmetric? See, whenever they ask you, they give you a matrix and they ask you to verify whether it is symmetric or not, simply take the matrix and apply transpose on that, my dear. And you know A plus B whole transpose is A transpose plus B transpose. And he says it is a symmetric matrix. Okay, he not mentioned it is symmetric, sir. It is just a square matrix. Sorry, it is just a square matrix. Okay, fine. Let us use that. A transpose whole transpose, you get it as A. And it is same as the original matrix. That is A plus A transpose whole transpose is same as A plus A transpose. Therefore, this fellow is a symmetric. Now let us try option B. What about A minus A transpose? Just apply transpose on it. So this is A transpose minus A transpose whole transpose. This is A transpose minus, and this can be written as minus of A minus A. Okay. So the transpose of the matrix is minus of the matrix, therefore it becomes skew symmetric. Now let us try option C. What about A into A transpose? Apply transpose on it. You know AB whole transpose is B transpose into A transpose. That is A transpose whole transpose is A and it is A into A transpose. Again you got the same matrix that is symmetric. And the final one is B transpose A. Apply transpose. See, whenever you apply transpose on the product, we get product of the transposed matrices in the reverse order. That is, you get B transpose, A transpose, B transpose, whole transpose. This is B transpose. This is A transpose. B transpose whole transpose is. Now the answer depend on the value of A, because when it is a square matrix A transpose, you can't say anything. So again, this depends on what is A. Suppose if A is symmetric, it becomes B transpose AB. So this B transpose AB becomes symmetric. Suppose if A is skew symmetric, A is if it is skew symmetric, then what happens? This becomes B transpose. A transpose becomes minus AB. So it becomes B transpose AB with a minus sign. It becomes a skew symmetric. So it depends on the value of A. You can't say anything about it. So, but the question is, which of the following are symmetric means AC are symmetric. Which of the following is following are skew symmetric means B is skew symmetric. What about B transpose AB? We can't say directly. It depends on whether A is symmetric or A is skew symmetric. If A is neither symmetric nor symmetric nor skew symmetric, pray God. That's it. So we have some beautiful properties. For every square matrix, A plus A transpose and A into A transpose are symmetric. A minus A transpose is skew symmetric. And if A is symmetric, any power of A you take it, that is also symmetric, and B transpose AB will be symmetric. And if A is skew symmetric, any odd power of A, because A power 2k plus 1, A power 2k, even if A becomes minus A, it becomes plus A only, because even power of minus A is plus A only. But that extra 1 is there, no, this fellow. This fellow will make it minus A, so it becomes skew symmetric. So, for any skew symmetric matrix, you take any odd power of it, that is also skew symmetric. Even power of it is nothing. You can't say anything. Okay, even power you can't say anything, sir. So don't say even power is symmetric. No, even power is nothing. We can't say anything. But odd power of any skew symmetric matrix is skew symmetric. And B transpose AB becomes skew symmetric when A is a skew symmetric. It depends on the value of A. And again, this was a very basic question, but this was asked in GATE, my dear friends. They given a matrix and they ask you to express it as sum of symmetric and skew symmetric. Actually, every square matrix can be written as sum of symmetric and skew symmetric. See, just now we seen this is a symmetric matrix and this is a skew symmetric matrix. So take half of this and half of this. Add them, you'll get back A. So every matrix, square matrix, can be represented as sum of a symmetric and skew symmetric. That is it. You can try this, my dear friends. This is A, no? So you just need to write half A plus A transpose, half A minus A transpose. That I am not doing. Please try that, my dear. The next one is orthogonal matrix. What do you mean by orthogonal matrix? A square matrix is called orthogonal matrix. Okay, it's actually given the result, given the definition first of all. A square matrix, first let us write down the definition. A square matrix A is orthogonal if A transpose is equal to A inverse. The transpose of the matrix is same as inverse of the matrix, then that matrix is called orthogonal matrix. And this is the beautiful result to check whether the given matrix is orthogonal or not. A real square matrix is orthogonal. A real square matrix is orthogonal if the rows or the columns, form orthonormal set. For example, suppose you are having a matrix whose columns are say xy. This fellow is orthogonal if and only if the x and y form orthonormal set. That is, length of x is equal to 1, length of y is equal to 1, and their dot product is. So whenever the matrix is orthogonal, the columns forms orthonormal set. Whenever columns forms orthonormal set, the matrix becomes orthogonal. Not only that, suppose consider the 3 by 3 matrix. Suppose x, y, z are the columns. And if this is orthogonal, the columns, not only columns, even rows forms the orthonormal set, sir, but we are mostly writing them as columns. So I am just discussing this. The columns becomes orthonormal, columns forms an orthonormal set. That is, length of x is 1, length of y is 1, length of z is 1. And the dot product of any two vectors will be. So this is about your orthogonal matrix, my dear. And how to identify whether the matrix is orthogonal or not? Just verify whether the columns or the rows are forming orthonormal set or not. This is one of the beautiful, powerful result, and there were 2 to 3 gate questions based on the same result, my dear. Okay, actually, that is definition, and this has to be written separately. Unfortunately, it was a printing error. Okay. Now he is asking whether it is orthogonal or not. The matrix is orthogonal or not. See, one method is, see, if the matrix is orthogonal, A transpose must be equal to A inverse. So what should happen? Normally, A into A inverse should be equal to identity. If it is orthogonal, what should happen? A into A transpose must be equal to identity. This is method 1. Using this method, you can verify whether it is orthogonal or not. The method 2 is, you just consider them as columns and check what these column fellows are doing. Check what is the length of x. Length of x, cos square theta plus sin square theta under root, or under root cos square theta plus sin square theta equal to 1. What is length of y? Under root minus sin square theta plus cos square equal to 1. And what about dot product? Minus cos theta sin theta plus sin theta cos theta 0. Because the columns are forming orthonormal set. Okay, the columns forms orthonormal set. What we conclude? This matrix is orthogonal. Therefore, matrix A is the idea clear? Now, this is wonderful question. He says this matrix is orthogonal. You need to find the values of A. And again, the columns, once he clearly mentioned it is an orthogonal matrix, means the columns, because A is orthogonal, the columns form an orthonormal set. Means what? You take length of any vector, it should be 1. Length of any column vector, it should be 1. And dot product of any two vectors be. Okay. We actually solved similar problem earlier, if you remember, sir. Similar problem we solved earlier. Okay. Where a matrix is given and he asks you to find A. So I told you, we have to consider the value of A, B, which satisfy all the conditions, not just one condition. Remember. So what I do is I use this condition x dot y is 0. That means dot product of these two. What is dot product? Denominator is 7 into 7, 49, fixed 326 minus 18, and this should be equal to 0. From this you get the value of A is 2. But if you take norm of x, A value, you get 2 values, plus minus 2. But plus 2 satisfy both the conditions, so we take A is equal to 2. Similarly, if you consider y dot z, that must be 0. Denominator is 49, numerator 12, 326, 6b, and that should be equal to 0. So what happens? 6b is equal to 18 minus 18. So b value is equal to. This is one of the important candidate question for your examination. Okay. Now this is also GATE question. Options also were given. He given this matrix is orthogonal matrix and he's asking what is the inverse of it. And you know what people done? For finding Q inverse, they done adjoint Q by determinant of. You can also find this solution in most of the PYQ solution books also. My dear friends, it is an orthogonal matrix. The inverse of the matrix must be just transpose of the matrix. Just transpose the matrix, you are going to get the orthogonal matrix. 1 by 9, 8 by 9, 4 by 9, minus 4 by 9, 4 by 9, 1 by 9, 4 by 9, minus 7 by 9, minus 4. Just transpose, you're going to get. Remember, of course, you don't even have to write, sir, because he given 4 options, you have to take the correct option. Now, we'll conclude today's session with this complex analogous, okay, definitions of what we just discussed, that is symmetric, skew symmetric, and orthogonal. First of all, what is a complex matrix, sir? A complex matrix is a matrix whose elements are complex numbers. You can also have real numbers, my dear friend. Okay. Now, what do you mean by conjugate? Replace conjugate of this matrix, replace every element by its conjugate. So it is 2 minus I, 3 plus 2I. Real number conjugate itself, and 1 minus I. And what about the conjugate transpose? After conjugate, you have to transpose the matrix. 2 minus I, 5, 3 plus 2I, and 1 minus. Okay. So some people call it as tranjugate, but I don't use such names, sir. Proper conjugate transpose is a better name. Okay. This is what you mean by conjugate transpose of a complex matrix. Now, what is Hermitian matrix? A complex square matrix is called Hermitian if its conjugate transpose is equal to matrix. Conjugate transpose, when you do it, you should get the same matrix. Then you call it as a Hermitian matrix. My dear friends, if all the elements of the matrix are real numbers, the conjugate of the matrix is matrix itself. So the conjugate transpose becomes simply transpose of the matrix. So this result reduces to symmetric matrix result, my dear. If the matrix is real matrix, the Hermitian matrix is exactly same as symmetric. In other words, symmetric matrix is a special case of Hermitian matrix. Symmetric matrix is a special case of Hermitian matrix. So for Hermitian matrix, there are two conditions. The main diagonals are real numbers, and secondly, Aij must be equal to Aji conjugate. You see in the mirror images of the main diagonal, they must be conjugates of each other. They must be conjugates of each other. Suppose if this fellow is 2 plus I, this fellow must be 2 minus. So it is very easy to identify Hermitian matrix, my dear friend. Or you can do one thing, you can try to construct Hermitian matrices on your own. Let us construct one Hermitian matrix. First condition is main diagonal must be real numbers. Any real number you can keep, sir. Okay, I'm just writing integers. You can also have negative fellows, no problem. Now here, whatever number is here, that fellow's conjugate is here. 3 minus 2i, then it is 3 plus 2. Suppose if I put 5, conjugate of 5 is 5 only. You can verify this. This is obviously a Hermitian matrix. Okay, this is a Hermitian matrix. What about a skew Hermitian matrix? A skew Hermitian matrix is a complex matrix, okay, satisfying the following condition. What is the condition? The conjugate transpose of the matrix is minus. Conjugate transpose is, okay. See, there are two conditions with which you can easily identify skew Hermitian matrix. The first one is the main diagonals are either pure imaginary or G. Either pure imaginary or, this is about the main diagonal. And second thing is Aij must be equal to minus Aji conjugate. Okay. See, the idea is, suppose if it is 2 plus I, the conjugate means, actually minus conjugate means real part sign is different, real imaginary part sign is same. So it should be minus 2 plus. See, the real part sign is different. You can try constructing a skew Hermitian matrix on your own, my dear. The main diagonal must be either purely imaginary or 0. Anything you can do. Whereas the off diagonal elements, what should happen? The mirror images must be minus conjugates of each other. Suppose if I put 2 plus I, it should be minus 2. Suppose if it is minus 3 minus 2i, then it is 3 minus 2. It is 5 minus. You can verify, sir, conjugate, transpose, you do it, it will be definitely minus of the matrix. Am I clear? So that is about skew Hermitian matrix, my dear. And the final one is unitary matrix. What about unitary matrix, sir? A complex square matrix is called unitary matrix if the transpose of the matrix is equal to inverse of the conjugate transpose, not just transpose, sir. Complex we always talk about conjugate transpose. The conjugate transpose must be equal to inverse of the matrix, my dear. So when you multiply with A conjugate transpose, normally A into A inverse is identity. If it is a unitary matrix, instead of A inverse, I can keep A conjugate transpose, but still I can get the matrix, my dear. So we don't have as such any such observations for this. Okay. But one important thing is the dot product for complex matrices. The normal matrices, normal column vectors, if you want to do dot product, it is uh, the first vector transpose into second vector. But u dot v for complex vectors is u transpose into, sorry, it's into dot, sorry, into v conjugate. This is how we get it. So the dot product for complex vectors, dot product for complex vectors. Okay. So you can also use this particular result for unitary matrices. A complex square matrices matrix is a unitary matrix if and only if the rows and columns forms orthonormal set with respect to complex inner product. The complex inner product means u dot v is, okay, u transpose into v conjugate. With respect to this complex inner product, it should form the orthonormal vectors. That is, length of vectors must be equal to 1 and dot product must be equal to 0. Both like 2 and other one is. See, the simple way of verifying this is, you can just check the vector u, which is 1 by 2, 1 by root 2, I by root 2. What about norm? See, norm of this is actually mod 1 by root 2 whole square plus mod I by root 2 whole square, sir. Please be careful. It is not whole square of the number. It is mod. The mod a plus ib is under root a square plus b square. So here mod I by root 2 whole square is, okay, mod means what, sir? It is under root, because a plus ib, no, a is 0. So 1 by root 2 whole square. Okay. And this fellow's whole square. So you get 1 by 2, my dear friends. So this is 1 by 2. This is 1 by root 2, na? So it is 1 by 2. So it is 1 by 2 plus 1 by 2. See, normally what people do, 1 by I by root 2 whole square, they do it, which is wrong, which gives you minus 1 by 2. That is wrong. Please be careful. It is mod I by root 2 whole square, which gives you 1. Similarly, length of v is equal to 1. And u dot v, if you want to do it, as I mentioned, it is u transpose into v conjugate. U transpose means 1 by root 2, I by root 2, the conjugate of this one. V fellows conjugate, that is minus I by root 2, 1 by root. When you do the multiplication, it is minus I by 2 plus I by 2. That is, the columns are forming orthonormal set with respect to complex inner product. Therefore, this matrix is unitary matrix. Or simply you can try this A into A conjugate transpose, sir. You should get identity. See, generally, people ignore this particular result. This can be done for even complex matrices, but only thing is, it is not regular inner product, complex inner. So this, with respect to this inner product, you have to try. Otherwise, you will get mistakes or errors. Please be careful. Here also people do mistake. It is mod I by root 2 whole square, not I by root 2 whole square. That again gives mistake. Please be careful, my dear. So this is about your second day session, that is square matrices. In tomorrow's session, we'll start with determinants, my dear friend. And on Saturday, the class will be in the evening session from 7 p.m. on. Saturday, we'll take class from 7 p.m., my dear friend. Okay. So if you have any doubts, you can ask me. Otherwise, that's all for today.